Hello everyone, welcome you all to the next session on relations and functions of class 12 mathematics. In this session, we'll solve a few more problems from exercise 1.3. Here is the fifth problem for us. State with reason whether following functions have inverse. This f from 1, 2, 3, 4 to the set 10 with f is equal to set containing 1, 10, 2, 10, 3, 10, 4, 10. And we have other two subdivisions also. What we are supposed to do here is we have to check whether the given functions has inverse or not. Let's solve the first subdivision here so that you can try out the remaining as a homework. The first subdivision here is you have a function, say f, from the set containing elements 1, 2, 3, 4 to the set containing element 10 with the definition f is equal to set containing the ordered pair 1, 10, 2, 10, 3, 10 and 4, 10. So as we were discussing in the previous sessions, when you have 1, 10 as an ordered pair, it means 1 is your input whereas 2 is the output. Similarly, we have 2, 10. This means 2 is our input whereas 10 is our output. So we have 3 as the input and 10 as the output. Similarly, 4 is the input and 10 is the output for the remaining. So here 1 is the input and 10 is the output. Now we can define from the definition of function. I can write f of 1 is 10, f of 2 is 10, f of 3 is 10, f of 4 is also 10. So we see that all the elements from the first set is mapped to the same element in the second set. That is, the images of the elements are not distinct, and hence we can conclude that f is not 1 to 1. Now as per the theorems and definitions that we have learned in the previous sessions, we know that a function can be invertible only when it is 1 to 1 and onto. The first condition itself fails here, that is our f is not 1 to 1, and hence the given function is not invertible. That means the given function does not have an inverse. This f does not have an inverse. So the first problem is solved. That is, we have found a reason whether the following has inverse or not. The first function given f does not have an inverse because f is not 1 to 1. So with this understanding, try out the remaining two subdivisions so that we can move on to the next problem now. The sixth problem says, show that f from the closed set minus 1, 1 to R, that is set of real numbers given by f of x is equal to x by x plus 2 is 1 to 1. Find the inverse of the function f from minus 1 to 1, that is a closed interval minus 1 to 1 to range f. There is a hint here. For every y belongs to range f, y is equal to f of x, that is equal to x by x plus 2 for some x in the closed interval minus 1, 1. That is, x is equal to 2y by 1 minus y. Let's come back to the hint later. Let's say the question what we have. We have a function f which is from the closed interval minus 1 to 1 to the set of real numbers defined by f of x is x by x plus 2. Now the first thing we have to show this function is 1 to 1. Let us finish off that and then come back to the next part of the problem. So we have f of x is x by x plus 2. Let us take two elements from the closed interval minus 1, 1, which is nothing but x and y. So we can say let x, y belongs to the closed interval minus 1, 1. Now we'll have a condition, say f of x is equal to f of y. We need to prove here is if f of x is equal to f of y, then it means x is equal to y. So let us assume f of x is equal to f of y. When f of x and f of y are equal, it means x by x plus 2 is equal to y by y plus 2. Obviously, the next step is to go for cross multiplication. I don't think I need to have a much explanation on this because we have discussed similar problems in our previous sessions. So x into y plus 2 equal to y into x plus 2. When you simplify this, that gives you x equal to y. That is, you will have xy plus 2x is equal to xy plus 2y. So xy and xy gets cancelled, leaving you 2x is equal to 2y, that gives you x is equal to y. So f of x equal to f of y implies x equal to y. This tells us f is 1 to 1. So the first part of the question is solved. That is, we have showed that the given function is 1 to 1. Now find the inverse of the function f from minus 1 to 1 to the range f. Now to find an inverse of a function, first thing I have to prove that the given function f is invertible, for which I have to prove f is 1 to 1 and also onto. The first part 1 to 1 is done, so let us prove the given function is onto also. And then we can confirm that it has an inverse, and then we'll try to find the inverse of this function. So you know the set, the function f is from set containing minus 1 to 1 to the set of real numbers. So whatever element you take from the set of real numbers, you will be able to find an element in the given set, because your f of x is x by x plus 2. So the element which you're going to take will definitely have an element in the closed interval minus 1 comma 1. So there need not be any explanation for it. So I can directly write for every y belongs to R, that is every y belongs to real numbers, there exists an x in the closed interval minus 1 to 1 such that f of x is equal to y, and I can conclude that f is onto. Now since f is onto, we'll have f of x is equal to y. That means your f of x is nothing but x by x plus 2. So this is by the definition. So we'll say y is equal to x by x plus 2, from which we'll get the value of x in this. So as we do the cross multiplication, we'll have y into x plus 2 equal to x. When we multiply, you can see the process here. Xy plus 2y equal to x. Have xy plus 2y equal to x. Then I'm bringing this x to the other side of the equation, which gives me xy plus 2y minus x equal to 0. And then factoring out, for which I'm rearranging, there is xy minus x plus 2y equal to 0. From these two, x is common, so x into y minus 1 plus 2y equal to 0. So we can have x is equal to, or I can write x into y minus 1 is equal to minus 2y. So x equal to minus 2y by y minus 1, or 2y by y 1 minus y. So the denominator has 1 minus y. We should not have y as 1 because your denominator becomes 0. So x equal to 2y by y 1 minus y is possible only when y is not equal to 1. So this tells us that for every element, for every element 2y by 1 minus y in your first set, that is a closed interval minus 1 comma 1, you have an element called x by x plus 2 in your R set of real numbers. So for every x, that is x is equal to, when every 2y by 1 minus y in your closed interval minus 1 comma, that is 2y by 1 minus y belongs to the closed interval minus 1 comma 1. So this can take every value except 1. For all these elements, you have an element called y, which is nothing but x by x plus 2, which is an element of the set of real numbers. So you are able to find an element, and hence because it is exactly onto, so we are able to find an element, and that element is in the form 2y by 1 minus y. Now what are we trying to do here? We have understood that f is 1 to 1, and we have proved f is onto, from which we are identifying the way the element in the first set looks like for us. That is the nature of the elements, that is pre-images. Now we have proved f is 1 to 1 and f is onto, which means that f is invertible. That is, inverse of the given function f is existing. And we are supposed to find, actually the question is, find the inverse of the function f from minus 1 to 1 to range f. The range of f, when we have an element like minus 1 to 1 to r, all the range of the elements will be of the form x by x plus 2. So we need to find an inverse from this set, that is minus 1 to 1 to range of f. Now I know that f is invertible, so I know that there is an inverse for the a given function. So let me consider the inverse as some g. That is, I'll name the inverse of the function as g, and let me try to find out what is this g. Now for which what I'm doing here is I'm assuming the given function, I'm assuming the function g, which is from the range f to the closed interval minus 1 comma 1, because this is how it has to be, because we have f from the closed interval minus 1 comma 1 to range f. Range f, or it is a set of real numbers. Sorry, it is a set of real numbers. And real numbers has range f. So range f is a subset of this real numbers. And if at all we define a function g from range f, that is range f is a subset of this. So range f to the closed interval minus 1 comma 1. So I can say, in this case I can say the function g will be inverse of f, provided I need to find out what exactly it is. So let me assume the function g in the form that is g of y is equal to 2y by 1 minus y, because g is defined from range of f to the closed interval minus 1 comma 1. So the range of f can have elements only in the form of 2y by 1 minus y. So we are going to define a function from this to this. Let me put it in a diagrammatic manner which will be more convenient for you to understand. And here it is. We have the first set here, and this is the second set. When I'm defining function f from this set to the other set, the elements here will be of the form 2y by 1 minus y, and here it is going to be x by x plus 2. Now the range for f is nothing but x by x plus 2. Now when I'm going to define a function g from range set to the closed interval, I will have it like it's going to be like this. That is, you have a function g, and this is from the range. So you will have the elements again x by x plus 2 will take the form 2y by 1 minus y. So this is the element, that is, this is your range. This is going to be actually range of f to the closed interval minus 1 comma 1. So this is how the function have been defined. So now I am assuming a function g in such a way that g of y is equal to 2y by 1 minus y, and I am going to prove this is the inverse of f. So for which I have to prove, if at all I have to prove g is the inverse, I can say g is 1 to 1 and on to, and I can prove g is invertible. But here I have to prove g is inverse of f, for which I am going to apply the composition of functions here. That is, I have to prove g composite f is an identity function. Similarly, f composite g is also an identity function. So if I prove this is possible, that is when a g composite f is equal to I of minus 1 comma 1. That is minus 1 comma 1 is a first set of f. Similarly, if I prove f composite g is equal to I of range f, that is a domain set of g, then I can say that f and g are inverses to each other, and hence I can conclude g is inverse of f. I hope you are able to understand. We have proved f is 1 to 1. We have also proved f is on to. This tells us that f is invertible and f has an inverse. Now we are in the verge of finding out what is the inverse of f, for which I am assuming a function g from the range of f to the closed interval minus 1 comma 1 defined by g of y is equal to 2y by 1 minus y. Now I have assumed a function g. Now I have to prove this is inverse of f, for which I am going to find the composition of this g with f, that is f composite g and g composite f, and I have to show both are identity functions. Only then I can conclude this g is the inverse of f. Now let us go for finding the composition of functions. Here is the first one, g composite f of x. It's as per the definition of composite functions. We can replace this composition by the brackets, that is g of f of x. Now f of x is nothing but x by x plus 2, that is g of x by x plus 2. Now the next one we have g of x by x plus 2. Now if at all I have if at all I have g of y that takes the form 2y by 1 minus y. That is, you can see the input y is multiplied by 2 in the numerator, and the denominator part, it is like 1 minus y. That is negative of y and 1 is added to it. So this is your definition for a g of y. Now here my input is not y, rather I am going to have x by x plus 2 as the input. So let me see what I am going to have it as an output. So the input into 2 will be the numerator. So input is x by x plus 2 into 2 is the numerator. And then what is the denominator? So denominator starts with the negative of this input first. So minus of x by x plus 2, and then 1 is added to it. I am putting it at the front. So this is how we have, I can even have a bracket here to not to be confusing with the sign. So I am adding a bracket here. So g of x by x plus 2 is equal to 2 times of x by x plus 2 divided by 1 minus of x by x plus 2. Now comes only simplification that we can do it. So here is a simplification. The numerator gives you 2x by x plus 2. Your denominator gives you x plus 2 minus x by x plus 2. So we have the denominator same, and for both numerator and denominator that gets cancelled out, which gives you 2x by 2. You can see this x and minus x goes off, 2x by 2, and here it is. So 2x by 2 is nothing but your x. So g composite f of x is equal to x implies g composite f is an identity function, and x is nothing but an element in the set minus 1 comma 1. So g composite f of x is equal to I of minus 1 comma 1. So the first part is done, that is proving g composite f is an identity function is done. Let's move on to the next one, that is proving f composite g. So f composite g of y, which is nothing but f of g of y. Why am I choosing y instead of x here? Is because f composite g is an element from range f to this. That is, you can see it here. So it will give you output only in the form of y. So I am choosing f composite g of y, which is nothing but f of g of y. G of y is, as we know, it is 2y by 1 minus y. That is, if you have a element, so we are just substituting g of y here. Let me write what is our f of x. Our f of x is nothing but x by x plus 2. That is, if your input is x, your output is going to be x in the numerator, whereas the denominator is x plus 2. That is, 2 is added to your input. That is your denominator part. Now let us work out the same concept for the input 2y by 1 minus y. That is f of 2y by 1 minus y. As we know, the numerator is going to be as such. So numerator of the output is going to be 2y by 1 minus y. And what is the denominator? Denominator has input, as such. It is 2y by 1 minus y is as such, and a 2 is added to it. So this is our x plus 2. So this is what we have it here. You can see from this step, the like f of g of y is nothing but 2y by 1 minus y divided by 2y by 1 minus y plus 2. Now comes a mere simplification. So you will have 2y by 1 minus y in the numerator, and denominator has 2y plus 2 minus 2y with the denominator 1 minus y. So we can see the denominator is getting cancelled, leaving you 2y by 2. That is, minus 2y and plus 2y gets cancelled, gives you 2y by 2. That is, f composite g of y is equal to y. So this tells you that f composite g of y is nothing but I of range f, that is identity function of range f. So we are done with the second part also, that is proving f composite g also an identity function. So we have proved g composite f is an identity function with the identity function of minus 1 comma 1, and f composite g is also an identity function with a range f. This means that f and g are both inverses of each other, or I could conclude g is the inverse of f, or f inverse, there is a symbol f inverse is equal to g, that is f inverse of y is equal to g of y. But we know what is g of y, this is what we have defined. So g of y is nothing but 2y by 1 minus y, hence f inverse of y is equal to 2y by 1 minus y, where your y is not equal to 1. So we have found the inverse of the given function. So this is what we are going to have it. Let me go back to the question and have a look at it once again. Show that function f from minus 1 to 1 to the set of real numbers given by f of x is x by x plus 2 is 1 to 1. Find the inverse of the function where f is from minus 1 to 1 to range f. So we have proved it like f is 1 to 1, for which we have assumed f of x and f of y are equal, and we got x is equal to y. With that we have proved f is 1 to 1. We have proved f is 1 to 1, and we are on the verge of proving f is on to. We have also proved that also. Here it is. So we have proved f is on to, and then we have the definition, that is f of x is equal to y because of f on to, from which we are getting the value of x, that is x in terms of y, which is nothing but x equal to 2y by 1 minus y, with the denominator y not equal to 1. So this we derive from the relation, from the understanding that f is on to. With this 2y by 1 minus y, we define a function g such that g of y is equal to 2y by 1 minus y, and this is defined from range f to the closed interval minus 1 comma 1. Now we have f is 1 to 1 and we have f is on to, hence f is invertible. So definitely there is going to be an inverse for f. Let us assume that inverse as g. And we are trying to prove this g is the inverse of f. There is a defined function. The function that is defined by g of y equal to 2y by 1 minus y is the inverse of f, is what we are going to prove it, for which we are finding the composition of both the functions f and g. That is both the composition g composite f and f composite g we have found, and we have proved that they both are an identity function. So with that understanding, we have proved that g is the inverse of f, that is nothing but 2y by 1 minus y is nothing but your f inverse of y. So f inverse of y is equal to 2y by 1 minus y, which is defined from the range f to set containing the closed interval minus 1 comma 1 is the inverse for the given function f. So with this I conclude the session, because the operations that we have learnt now is not very easy. So take your time to go through the entire steps so that you'll be able to do the homework problems for the day. Here are the homework problems. Question number 5, the remaining two subdivisions. We have already discussed the first subdivision. You can try out the remaining two subdivisions. And question number 7 and 8, it is almost similar to the question 6. So try out. You have different operations. Here we had rational numbers, that is x by x plus 2. You'll be having with the square root something. So try it out. If you have any doubt, please message us. I'll help you to solve it out. We'll meet you in the next session with the next set of problems from the same exercise. Thank you.